There is an object in the universe so massive that if you replaced our Sun with it, its edge would swallow every planet, every asteroid, every comet, and still reach beyond the orbit of Pluto. This object contains the mass of 66 billion suns crushed into a sphere of absolute darkness. Light cannot escape it. Time warps around it. Space itself bends toward its center in ways that break human intuition. Scientists call it TON 618, and it represents the most massive black hole ever measured by human instruments. But what does it actually mean to be the largest black hole? How do we weigh something we cannot see? And what does this cosmic monster reveal about the fundamental architecture of our universe? If you enjoy journeys that fundamentally reshape how you see reality, consider hitting that like button and subscribing to join us on more cosmic explorations. Now, settle in and get yourself comfortable. Let's begin. Black holes come in sizes that span a range almost impossible to comprehend. The smallest confirmed black holes contain roughly 3 times the mass of our Sun, compressed into spheres smaller than a city. The largest contain masses equivalent to tens of billions of stars, occupying regions of space larger than our entire solar system. Between these extremes lies a hierarchy of gravitational monsters that astronomers have spent decades mapping and measuring. Understanding what makes a black hole the largest requires first understanding what astronomers actually measure when they study these invisible objects. A black hole possesses no surface in the conventional sense. It has no solid boundary, no rocky exterior, no gaseous atmosphere. What defines a black hole is its event horizon, the mathematical boundary beyond which nothing, not even light travelling at 300,000 kilometers per second, can escape the gravitational pull toward the central singularity. The event horizon represents something profound in physics. It marks the point where the escape velocity equals the speed of light. Any object crossing this threshold, whether a spacecraft, a particle of dust, or a beam of light itself, becomes permanently trapped. The boundary does not consist of any physical material. You could cross an event horizon without feeling anything unusual at the moment of crossing. But once inside, every possible trajectory through space-time leads inexorably toward the center. There is no direction called outward anymore. The size of this event horizon depends entirely on mass. More mass means stronger gravitational pull, which means the event horizon extends farther from the center. This relationship follows a precise mathematical formula, first calculated by Carl Schwarzschild in 1916, just months after Einstein published his general theory of relativity. Schwarzschild solved Einstein's field equations for a spherical, non-rotating mass, deriving the radius at which the event horizon would form. This Schwarzschild radius, as it became known, tells us exactly how large an event horizon will be for any given amount of mass. For our Sun, hypothetically compressed into a black hole, the Schwarzschild radius would measure approximately 3 kilometers. The entire mass of our star, 1 million times the volume of Earth, would create an event horizon smaller than many asteroids. You could drive around it in less than an hour. For a black hole containing 10 solar masses, the kind produced when a massive star exhausts its nuclear fuel and collapses, the event horizon expands to roughly 30 kilometers, still small enough to fit within the boundaries of a major city. The relationship scales linearly. Double the mass, double the radius. This simple proportionality becomes critically important when we consider the truly massive black holes lurking at the centers of galaxies. A black hole containing 1 million solar masses would have an event horizon roughly 3 million kilometers across, comparable to 5 times the radius of our Sun. At 1 billion solar masses, the event horizon stretches to nearly 3 billion kilometers, approaching the orbital distance of Uranus from the Sun. The black hole would swallow the inner solar system entirely. Astronomers classify black holes into distinct categories based on their mass, creating a taxonomy of gravitational monsters. Stellar mass black holes form from the collapsed cores of massive stars and typically range from 3 to perhaps 100 solar masses. These represent the endpoints of stellar evolution for the most massive stars, objects that burn through their nuclear fuel in just a few million years before gravity crushed their cores beyond any possible resistance. Intermediate mass black holes occupy a mysterious middle ground. If they exist in significant numbers, they would contain between roughly 100 and 100,000 solar masses. These objects remain elusive, with only a handful of candidates detected through gravitational wave observations and careful analysis of star cluster dynamics. Their scarcity poses a puzzle that astronomers continue working to resolve. Supermassive black holes contain millions to billions of solar masses and reside at the centers of most large galaxies. Nearly every galaxy with a substantial bulge appears to harbor one of these gravitational giants at its core. Our own Milky Way contains Sagittarius A star, a supermassive black hole of approximately 4 million solar masses. The Andromeda Galaxy hosts an even larger specimen of roughly 100 million solar masses. These objects appear fundamental to galactic structure, though the precise relationship between black hole and host galaxy remains an active area of research. Beyond even these giants lie the ultramassive black holes, objects containing tens of billions of solar masses that push the boundaries of what current physics can explain. These extreme specimens raise immediate questions about formation mechanisms and growth timescales. How can anything accumulate such tremendous mass? What cosmic processes could feed such voracious gravitational engines? TON 618 belongs to this final category. Located approximately 10.4 billion light-years from Earth, in the constellation Canes Venatici, this object represents the most massive black hole that astronomers have successfully measured using current techniques. The estimated mass hovers around 66 billion solar masses, though uncertainties in the measurement methods mean this figure could range somewhat higher or lower. Even the conservative estimates place this object among the most extreme gravitational concentrations in the observable universe. The designation TON 618 derives from the Tonantzintla Observatory in Mexico, where astronomers first catalogued this object during a survey of blue stellar objects in the 1950s and 60s. At that time, nobody understood what they were observing. The object appeared as merely another point of light in a sky full of stars, distinguished only by its unusual blue colour and slight fuzziness in photographic plates. Only later did astronomers recognize TON 618 as a quasar, one of the most luminous objects in the universe. Quasars are active galactic nuclei powered by supermassive black holes, consuming surrounding matter at prodigious rates. The intense radiation emerges not from the black hole itself, which remains utterly dark, but from superheated material spiraling inward through an accretion disk. This process converts gravitational potential energy into electromagnetic radiation with efficiency that dwarfs nuclear fusion. To begin grasping what 66 billion solar masses actually represents, consider the following progression. Our Sun contains enough mass to create roughly 333,000 Earths. Every rock, every ocean, every wisp of atmosphere on our planet represents merely 3/millionths of the Sun's total mass. A black hole of 10 solar masses, the kind produced by a supernova explosion, contains mass equivalent to over 3 million Earths. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star, contains approximately 4 million solar masses, equivalent to over 1 trillion Earths. TON 618 contains more than 16,000 times the mass of Sagittarius A star. If our galaxy's central black hole represents a large boulder, TON 618 represents an entire mountain range extending beyond the horizon in every direction. The comparison fails not because it exaggerates, but because human experience provides no adequate reference for such scaling. We evolved to understand masses we could lift, distances we could walk, timescales matching human lifespans. Nothing in our evolutionary history prepared us to comprehend objects containing 66 billion solar masses. Consider another approach to this scale. If you could somehow count the mass of TON 618 in units of Earth masses, counting 1 Earth per second without stopping to eat, sleep, or rest, You would need approximately 700 trillion years to complete the count. That duration exceeds the current age of the universe by a factor of 50,000. The number is so large that even astronomical timescales prove inadequate for comprehension. The event horizon of TON 618 extends to approximately 1,300 astronomical units from its center. 1 astronomical unit equals the average distance between Earth and the Sun, roughly 150 million kilometers. This means the boundary of the event horizon lies more than 40 times farther from its center than Neptune orbits from our Sun. The entire solar system, from Mercury's close orbit around the Sun through the rocky inner planets, past the gas giants, beyond the ice giants, all the way to the Kuiper belt where Pluto traces its elongated path, would fit comfortably within this single object's event horizon with room to spare. If you replaced our Sun with TON 618, the event horizon would extend past every planet. Voyager 1, the most distant human-made object, launched in 1977 and now over 150 astronomical units from the Sun, after decades of travel, would still be falling toward the center. The entire realm that constitutes our cosmic neighborhood would simply vanish behind a horizon of absolute darkness. Yet mass, not physical size, defines what makes TON 618 the largest black hole. A common misconception treats black holes as objects with measurable volumes, but the event horizon encloses a region of space, not a solid body. The interior of a black hole is not like the interior of a planet or star. It is a region where our normal understanding of space and time breaks down completely. What matters is the gravitational influence this mass exerts, the way it warps space-time, bends light, and dominates the motion of matter across distances that dwarf individual star systems. This gravitational influence extends far beyond the event horizon itself. The sphere of gravitational dominance, where the black hole's gravity overpowers other influences, can stretch for thousands or even millions of light years around the most massive specimens. Within this region, stars, gas clouds, and even smaller galaxies feel the inexorable pull toward the central mass. The black hole may be invisible, but its presence shapes the structure of everything around it. Einstein's general theory of relativity describes gravity not as a force in the conventional sense, but as the curvature of space-time caused by mass and energy. Massive objects create depressions in the fabric of space-time, and other objects follow the curved paths these depressions create. Near a black hole, the curvature becomes so extreme that space-time folds in on itself. The event horizon marks the point where this folding becomes complete, where all paths lead inward regardless of direction or velocity. The history of black hole mass measurement reveals how dramatically our understanding has evolved over just a few decades. When astronomers first detected quasars in the 1960s, they recognized these brilliant points of light as extraordinarily distant and extraordinarily luminous. The energy output seemed impossible to explain through any known process. A single quasar could outshine its entire host galaxy by factors of hundreds or thousands, yet appeared as a mere point of light even in the most powerful telescopes. Only gradually did the scientific community accept that supermassive black holes, actively consuming surrounding matter, could generate such tremendous power. The concept seemed almost too extreme. Black holes had been theoretical curiosities since Schwarzschild's calculations, but nobody expected them to exist at such scales or to play such important roles in cosmic evolution. The acceptance of supermassive black holes as real objects rather than mathematical abstractions required decades of accumulated evidence. The first reliable mass estimates for supermassive black holes came in the 1970s and 80s, using the motions of stars and gas near galactic centers. If you can measure how fast material orbits a central point, and you know how far that material sits from the center, basic physics allows you to calculate the mass doing the pulling. These early measurements revealed objects containing millions of solar masses, already challenging to explain through conventional stellar evolution. No single star could ever reach such masses. Something else had to be responsible. As techniques improved and observations extended to more distant galaxies, The upper limit of black hole mass kept climbing. Millions became billions. The largest local examples reached masses of 10 billion solar masses or more. Each new record prompted theorists to explain how such extreme objects could form and grow within the available cosmic time. TON 618 first attracted serious attention because of its extraordinary luminosity. Identified initially through optical surveys at Tonantzintla Observatory in Mexico during the 1950s and 60s, further observations revealed it as one of the most luminous quasars known. The object shines with the power of 140 trillion suns, visible across most of the observable universe despite lying at such extreme distance. This brightness suggested an extremely massive central engine, driving astronomers to attempt direct mass measurements despite the object's tremendous remoteness. The challenge of measuring black hole mass at cosmological distances cannot be overstated. Light from TON 618 has travelled for over 10 billion years to reach our telescopes. We see this object as it existed when the universe was only a few billion years old, far younger than its current age of approximately 13.8 billion years. The universe has changed profoundly during that journey. Galaxies have formed and evolved, stars have been born, lived and died. Our own solar system did not exist when this light began its voyage toward what would eventually become Earth. Any measurement must account for this temporal displacement and the cosmic expansion that has stretched space itself during the light's journey. The light arrives redshifted, its wavelengths elongated by the expansion of the universe. The object itself has been carried to even greater distances by this same expansion. The physics involved in extracting meaningful measurements from such ancient, stretched, faint light represents one of observational astronomy's greatest achievements. Different measurement techniques yield different results, and astronomers must carefully consider the systematic uncertainties inherent in each approach. The mass estimate for TON 618 comes primarily from analysing the motion of gas in its vicinity, using spectroscopic observations that reveal how quickly material orbits the central object. Light from this orbiting gas shows characteristic signatures of motion. Material moving toward us appears blue-shifted. Material moving away appears red-shifted. The spread in these shifts reveals the range of velocities present in the system. Faster orbital velocities at a given distance indicate greater central mass. This principle follows directly from Newton's laws of gravity, extended through Einstein's relativistic corrections for extreme gravitational fields. By measuring the velocity spread and estimating the size of the emitting region, astronomers can calculate the mass required to keep this material in orbit rather than flying off into space. This method assumes that the orbiting material follows predictable paths governed primarily by gravity. If other forces significantly influence the gas motion, such as radiation pressure from the brilliant accretion disk or magnetic fields threading through the system, or if the geometry of the system differs from assumptions built into the analysis, the resulting mass estimate could shift substantially. Scientists working with these measurements always report uncertainty ranges that acknowledge these potential sources of error. The currently accepted mass range for TON 618 spans from roughly 40 billion to over 66 billion solar masses, depending on which observational datasets and analytical methods researchers employ. The commonly cited figure of 66 billion solar masses represents the upper end of credible estimates, though it remains consistent with the best available data. Future observations with more powerful instruments may narrow this range, but significant uncertainty will likely persist given the fundamental challenges of measuring objects at such extreme distances. Even at the lower bound of 40 billion solar masses, TON 618 would still rank among the most massive black holes ever detected. The object belongs firmly in the ultramassive category regardless of where the true value falls within the estimated range. Debates about whether it contains 66 billion or 40 billion solar masses, while important for theoretical modelling, do not change its status as an extreme outlier in the cosmic population. The distinction between largest and most massive matters here, though the two concepts relate closely. Some black holes may have larger event horizons if they spin rapidly, which distorts the space-time geometry in ways that extend the boundary of no return. A maximally spinning black hole of a given mass would have an event horizon roughly twice as large as a non-spinning black hole of the same mass. But mass remains the fundamental quantity that determines gravitational influence and cosmic significance. Mass tells us how much space-time curves around the object, how strongly it pulls on surrounding matter, how much energy accreting material can release. Comparing TON 618 to other measured black holes reveals its exceptional nature. The supermassive black hole in Messier 87, famously imaged by the Event Horizon Telescope in 2019, contains approximately 6.5 billion solar masses. That historic image, showing a ring of light surrounding a dark central shadow, represented humanity's first direct look at the immediate environment of a black hole. The Messier 87 black hole is enormous by any reasonable standard, yet TON 618 contains roughly 10 times more mass. The object in Messier 87 would need to grow tenfold to match the estimated mass of TON 618. The black hole in NGC 4889, one of the most massive in the relatively local universe at roughly 300 million light-years distant, contains approximately 21 billion solar masses based on stellar dynamical measurements. This object ranks among the heaviest black holes close enough for detailed study. Yet even this giant amounts to only about 1/3 of TON 618's estimated mass. The most extreme black holes in our cosmic neighborhood appear modest compared to what exists at greater distances. Understanding black hole mass also requires recognizing what astronomers cannot directly observe. No telescope sees the black hole itself. The event horizon emits no light, reflects no radiation, produces no signal that any instrument could detect. The black hole reveals its presence only through gravitational effects on surrounding matter. Every black hole mass measurement relies on indirect evidence, tracing the influence of an invisible object through the behavior of visible material nearby. This indirect approach introduces unavoidable uncertainties that honest scientific discussion must acknowledge. When astronomers report the mass of TON 618 as 66 billion solar masses, they are not claiming precise knowledge of an exactly determined quantity. They are reporting the best estimate derivable from current data using current methods, with the explicit understanding that future observations and refined techniques may adjust this figure. Science progresses through such refinement, and the willingness to revise estimates in light of new evidence represents a strength rather than a weakness. The very concept of weighing a black hole across 10 billion light-years of space would have seemed impossible to scientists just decades ago. The techniques that make such measurements possible represent remarkable achievements of observational astronomy and theoretical physics working together. Spectroscopic analysis, understanding of quasar structure, models of accretion, disk physics, and cosmological distance calculations all combine to enable these measurements. Each component carries its own uncertainties that propagate through to the final result. Yet the inherent limitations of these methods mean that extreme black hole masses always carry significant uncertainty. The most massive objects sit at the limits of observational capability, where systematic errors become difficult to characterize, and random noise in the data contributes substantially to the final uncertainty range. Claims of precise masses for the most extreme black holes should always be understood as estimates rather than exact determinations. What remains beyond dispute is that TON 618 belongs to a class of ultramassive black holes that exist at the extreme end of the mass distribution. Whether it contains exactly 66 billion solar masses or somewhat more or less, it represents one of the most massive single objects that current instruments can detect and measure. The object sits firmly in rarefied territory, occupying a region of parameter space where only a handful of other known objects reside. The existence of such objects raises immediate questions that the following sections will explore. How can something grow so massive within the finite age of the universe? What does a black hole of this scale actually look like to surrounding space? And how does it influence matter across vast distances? How do scientists actually perform these measurements across cosmological distances? And what are the limits of our knowledge? And what does finding such extreme objects tell us about the universe's structure and history? The answers reveal a cosmos filled with gravitational engines of almost incomprehensible power, shaping the evolution of galaxies across billions of years, while remaining forever hidden behind horizons from which no information can escape. TON 618 stands as the most extreme example currently known, a benchmark against which other massive black holes are measured. But it may represent merely the most massive object we have managed to measure, rather than the most massive object that exists. The universe is vast, and our surveys remain incomplete. Somewhere beyond our current observational reach, even larger gravitational monsters may lurk in the darkness, waiting for future generations of telescopes to reveal their presence. The scale of TON 618 challenges not just our instruments, but our imagination. We can write the numbers, perform the calculations, and draw the comparisons. But truly comprehending an object that would swallow our entire solar system, that contains more mass than most galaxies possess in total stars, that warps space-time across distances measured in light years, remains beyond intuitive human grasp. Perhaps that is appropriate. The universe operates at scales that evolution never prepared us to understand. Our ability to measure and describe such objects, even if we cannot truly comprehend them, represents one of the remarkable achievements of the scientific enterprise. The event horizon of TON 618 defines a boundary in space-time that extends approximately 200 billion kilometers from the central singularity. To cross from one side of this boundary to the other, light would require roughly 15 days of continuous travel, assuming it could somehow traverse horizontally rather than falling inexorably inward. This duration exceeds the time light needs to travel from the Sun to Pluto and back again. The boundary of no return around this single object spans a diameter larger than any structure in our solar system by orders of magnitude. Within this spherical region, the geometry of space curves so severely that all possible paths lead toward the center. This statement requires careful understanding. It does not mean that some force pulls objects inward while they struggle to escape. It means that space-time itself has folded in such a way that the concept of outward no longer exists. Every direction, including what appears to be straight up or sideways or backward, actually points toward the singularity. The event horizon marks the surface where this geometric prison closes completely. An observer falling through the event horizon of TON 618 would notice nothing unusual at the moment of crossing. No barrier exists to penetrate. No sensation marks the transition. The mathematics of general relativity predicts a smooth passage across this threshold, at least for an observer in freefall. Yet that observer has now entered a region from which no return is possible, no signal can escape, and the future contains only one destination. The crossing is irreversible in the most absolute sense physics allows. The scale of this event horizon creates conditions unlike anything in our cosmic neighborhood. Light orbiting just outside the boundary follows paths curved so severely that photons can circle the black hole multiple times before escaping or falling in. This region, sometimes called the photon sphere, exists at roughly 1.5 times the Schwarzschild radius for a non-rotating black hole. For TON 618, this corresponds to a shell of unstable light orbits extending across hundreds of billions of kilometers. Surrounding this sphere of absolute darkness spins an accretion disk of incomprehensible scale and luminosity. Matter falling toward TON 618 does not simply drop straight in like a stone falling into a well. Conservation of angular momentum, the same principle that keeps planets in orbit rather than spiraling into the Sun, causes infalling material to spiral inward along gradually tightening paths. This spiraling motion forms a flattened disk structure that can extend for light years beyond the event horizon itself. The accretion disk represents where the black hole makes its presence known to the universe. The event horizon remains utterly dark, emitting nothing, reflecting nothing. But the disk blazes with radiation across the entire electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, X-rays, and even gamma rays. This emission makes TON 618 visible across most of the observable universe despite its tremendous distance. Friction within the accretion disk heats the material to temperatures exceeding tens of millions of degrees in the innermost regions. This heating occurs because material at different distances from the center orbits at different velocities. Inner material moves faster than outer material. Where these differentially moving layers contact each other, viscous friction converts orbital energy into heat. The disk glows because angular momentum must be transported outward for material to spiral inward, and this transport process inevitably generates thermal energy. The accretion disk around TON 618 produces energy output that beggars the luminosity of entire galaxies. Conservative estimates based on observed brightness suggest the total power exceeds 140 trillion times the energy output of our Sun. Written in scientific notation, this approaches 10 to the 14th solar luminosities. The entire Milky Way galaxy, containing 400 billion stars of various sizes and luminosities, produces total light output roughly 100 billion times that of the Sun. TON 618's accretion disk outshines our entire galaxy by a factor of more than 1,000. This places TON 618 among the most luminous quasars ever observed. The object functions as a cosmic beacon, visible across most of the observable universe despite lying over 10 billion light-years away. Ancient astronomers could have detected this object with sufficiently powerful telescopes, though its light would have shown them the universe as it existed long before Earth formed. The photons reaching our instruments tonight began their journey when the cosmos was less than a quarter of its present age. This luminosity emerges not from the black hole itself, which remains utterly dark, but from the transformation of gravitational potential energy into radiation as matter spirals inward. Consider a particle of gas beginning its descent toward the event horizon. As it falls deeper into the gravitational well, it accelerates. This acceleration represents the conversion of gravitational potential energy into kinetic energy. Through collisions and friction within the disk, this kinetic energy transforms into thermal energy, and hot material radiates. The efficiency of this process defies easy comprehension. Nuclear fusion, the energy source that powers stars including our Sun, converts roughly 0.7% of input mass into energy. This already represents an impressive achievement. The atomic bombs that ended World War II converted less than 1 gram of matter into the explosive energy that devastated entire cities. Stars sustain this process continuously for billions of years, and yet they tap less than 1% of the available mass energy. Accretion onto a black hole can convert up to 40% of infalling mass into radiation, depending on the black hole's spin and the precise geometry of the accretion disk. For maximally spinning black holes, where the innermost stable orbit approaches the event horizon most closely, the efficiency can reach toward this theoretical maximum. Even conservative estimates suggest efficiencies of 10 to 20%, still more than an order of magnitude greater than nuclear fusion. This extraordinary efficiency explains how a relatively modest amount of infalling material can produce luminosities that outshine hundreds of billions of stars simultaneously. TON 618 need not consume entire galaxies' worth of material each year to maintain its observed brightness. A few hundred solar masses of gas per year, falling inward through the accretion disk and converting a fraction of its mass to radiation, suffices to power this cosmic lighthouse. The inner edge of the accretion disk orbits TON 618 at velocities approaching a significant fraction of light speed. For a non-spinning black hole, the innermost stable circular orbit lies at 3 times the Schwarzschild radius. Material closer than this cannot maintain stable orbits and rapidly spirals inward. For TON 618, this innermost stable orbit still lies at tremendous distance from the center by human standards, yet the orbital velocities there reach tens of thousands of kilometers per second. Material at this inner boundary experiences relativistic effects that profoundly alter the physics of the environment. Gravitational time dilation causes clocks to run slower near massive objects. At the inner edge of the accretion disk around TON 618, time passes measurably slower than in regions far from the black hole. An observer stationed at this location, if such a position could be maintained, would age more slowly than a distant observer watching from intergalactic space. Relativistic length contraction and frame dragging add additional complexity. If TON 618 rotates, which most massive black holes are expected to do, the rotation drags space-time itself around with the spinning mass. This frame dragging effect, predicted by general relativity and confirmed through satellite experiments around Earth, reaches extreme intensities near rotating black holes. The accretion disk does not merely orbit through static space, it orbits through space that itself moves, carried along by the rotating mass within. An observer watching the inner accretion disk from a safe distance would see strange optical effects. Material approaching the event horizon appears to slow down due to gravitational time dilation. From the external perspective, infalling material takes longer and longer to reach the horizon, asymptotically approaching, but never quite crossing. Simultaneously, light from this material becomes increasingly redshifted as gravitational redshift stretches wavelengths toward infinity. The material appears to freeze and fade, growing dimmer and redder until it becomes undetectable, though from its own perspective it crosses the horizon in finite time. The accretion process around TON 618 does not proceed quietly. Magnetic fields thread through the ionized plasma of the accretion disk, and the differential rotation of the disk material twists and amplifies these fields enormously. The magnetorotational instability, identified theoretically in the 1990s, explains how magnetic fields create the turbulent viscosity necessary for accretion to proceed. Without magnetic fields, the disk would simply orbit indefinitely without material spiraling inward. These amplified magnetic structures can launch jets of plasma outward along the rotation axis at velocities approaching 99% of light speed. The precise mechanism remains an active area of research, but the basic picture involves magnetic field lines, threading the inner accretion disk, and possibly the event horizon itself. Rotation winds these field lines into tight spirals that accelerate plasma outward along the poles, creating collimated beams of relativistic particles that can extend for enormous distances. Such jets extend for thousands or even millions of light years beyond the host galaxy, depositing energy into intergalactic space and influencing the evolution of the entire surrounding cosmic environment. The power carried by these jets can rival or exceed the radiative luminosity of the accretion disk itself. They represent one of the most important mechanisms by which supermassive black holes affect matter far beyond their immediate gravitational reach. Evidence suggests TON 618 produces such jets, though the extreme distance makes detailed study challenging. Radio observations reveal extended emission consistent with jet activity, indicating that this black hole actively influences matter far beyond its immediate gravitational sphere. The radio lobes created by jets impacting intergalactic gas can span megaparsecs, structures so large that light requires millions of years to cross them. The energy deposited by these jets can heat intergalactic gas to temperatures that prevent it from cooling and collapsing into new galaxies. This feedback process, as astronomers term it, may explain why galaxy clusters contain far less star formation than naive predictions would suggest. The central supermassive black hole, through its jet activity, regulates the thermodynamic state of gas across volumes thousands of times larger than the host galaxy itself. Jets from active galactic nuclei can also trigger star formation under certain conditions. Where jets impact dense gas clouds, compression can initiate gravitational collapse, leading to new stellar birth. This positive feedback contrasts with the heating effect that suppresses star formation elsewhere. The net impact of jet activity on cosmic star formation rates involves this complex interplay between triggering and suppressing mechanisms. For TON 618 specifically, the jet power potentially exceeds 10 to the 47th ergs per second, comparable to the most powerful jets known from any cosmic source. This energy output, sustained over hundreds of millions of years of active phases, would deposit enough energy into the surrounding environment to significantly affect the evolution of an entire galaxy cluster. The black hole at the center influences the fate of trillions of stars that will never come close to its event horizon. The gravitational influence of TON 618 extends far beyond its event horizon and immediate accretion disk. The sphere within which this black hole's gravity dominates over other influences, sometimes called the sphere of influence, likely extends for hundreds of light-years in radius. This distance represents where the orbital velocity due to the black hole's mass equals the typical stellar velocity dispersion in the surrounding galactic bulge. Within this sphere of influence, stars orbit the central mass directly. Their paths trace ellipses around the black hole just as planets trace ellipses around the Sun, though the velocities involved far exceed anything in our solar system. Stars at tens of light-years from TON 618 might orbit at thousands of kilometers per second, completing full orbits in just thousands of years. These stellar motions, if they could be resolved observationally, would provide the most direct measurements of the central mass. Beyond the sphere of direct gravitational dominance, the influence of TON 618 persists in subtler forms. The mass distribution of the entire host galaxy must accommodate this enormous central concentration. A galaxy is not simply a collection of stars orbiting a common center. It represents a self-gravitating system where the distribution of mass determines the distribution of orbits. Inserting 66 billion solar masses at the center fundamentally alters this balance. Stars throughout the galaxy follow orbits influenced by the presence of such an extreme central mass. The velocity dispersion of stars in the galactic bulge, meaning the spread of stellar velocities in random directions, correlates with central black hole mass across thousands of measured galaxies. This correlation, discovered observationally before it was explained theoretically, suggests that black holes and their host galaxies grow together through linked processes. The dynamics of gas flows, the rates of star formation, and the structural evolution of the galactic bulge all reflect the gravitational reality imposed by this ultramassive black hole. Gas attempting to fall toward the galactic center must contend with the intense gravitational field. Tidal forces from the black hole can disrupt gas clouds, preventing the formation of massive molecular complexes that would otherwise spawn new stars. The mere presence of such concentrated mass shapes the evolutionary trajectory of the entire galaxy. The host galaxy of TON 618 remains poorly characterized due to the overwhelming luminosity of the central quasar. The brilliant accretion disk outshines the surrounding stellar population by enormous factors, making direct observation of the galaxy's structure extremely difficult. Imagine trying to study a candle flame positioned directly in front of a searchlight. The contrast ratio defeats attempts to characterize the fainter component. Based on relationships observed in other systems, astronomers expect the host to be an extremely massive elliptical galaxy, likely containing trillions of stars and residing at the center of a substantial galaxy cluster. These expectations arise from the observed correlation between black hole mass and host galaxy properties. More massive black holes inhabit more massive galaxies, following a relationship that holds across several orders of magnitude in mass. This correlation implies specific properties for any galaxy hosting a black hole of 66 billion solar masses. The most massive galaxies known contain stellar masses approaching 10 trillion solar masses. Giant elliptical galaxies at the centers of rich galaxy clusters can reach such extreme masses, built up through countless mergers over cosmic time. A black hole of 66 billion solar masses would represent roughly 0.7% of such a host galaxy's total stellar mass, consistent with observed relationships in lower mass systems where both components can be measured. The physical reality surrounding TON 618 includes phenomena that exist nowhere else in the local universe at comparable scales. The gravitational potential well reaches depths that create measurable time dilation effects extending far beyond the event horizon. General relativity predicts that clocks run slower in stronger gravitational fields, an effect confirmed by comparing atomic clocks at different altitudes on Earth and verified to high precision by GPS satellites. Near TON 618, this gravitational time dilation becomes extreme. An observer stationed 1 light-year from the center would experience time passing noticeably slower than an observer in intergalactic space, though still far from the extreme dilation encountered at the event horizon itself. At 100 astronomical units from the center, roughly the inner edge of a hypothetical surrounding stellar population, the time dilation would be more pronounced. At the inner edge of the accretion disk, clocks would run at rates significantly different from distant reference clocks. Space itself becomes distorted around such massive objects in ways that affect the propagation of light from background sources. TON 618 acts as a gravitational lens, bending light rays that pass near it and potentially creating multiple images of more distant objects. This lensing effect arises directly from general relativity's description of gravity as space-time curvature. Light follows the shortest path through curved space-time, and these paths bend around massive objects. Strong gravitational lensing near TON 618 could produce dramatic effects for perfectly aligned background sources. Einstein rings, where a background galaxy appears as a ring of light surrounding the foreground mass, or multiple distinct images of a single source, could theoretically be observed. However, the extreme distance and bright central emission from the quasar itself complicate such observations. The light from the accretion disk overwhelms the much fainter lensed images that might otherwise be detectable. Weak gravitational lensing, the subtle distortion of background galaxy shapes by foreground mass, provides another potential probe of the mass distribution. By statistically analyzing the shapes of many background galaxies, astronomers can reconstruct the mass distribution responsible for the observed distortions. This technique has proven powerful for mapping dark matter in galaxy clusters and could in principle constrain the mass profile around objects like TON 618, though observational challenges remain substantial. The temperature structure within the accretion disk follows predictable patterns that astronomers can model and compare against observations. The standard thin disk model, developed theoretically in the 1970s, predicts how temperature varies with radius in a viscously spreading accretion disk. Outer disk regions remain relatively cool, reaching temperatures of perhaps 10,000 degrees, similar to hot stellar surfaces. The disk at these distances resembles a very hot, but otherwise somewhat ordinary astronomical object. Moving inward, temperatures climb progressively as the gravitational potential well deepens and viscous dissipation increases. At intermediate radii, temperatures reach hundreds of thousands of degrees. The innermost regions before material crosses the event horizon achieve millions of degrees, temperatures that exceed the cores of ordinary stars. This temperature gradient produces a characteristic spectrum of radiation that helps distinguish active black hole accretion from other luminous phenomena. Observations of TON 618 across multiple wavelengths reveal emission consistent with these theoretical predictions. Infrared radiation emerges from cooler outer disk regions where temperatures match those of warm stellar atmospheres. Optical and ultraviolet light dominates the intermediate temperature zones, where the accretion disk reaches tens of thousands of degrees. X-ray emission traces the hottest inner disk areas where temperatures exceed what any stellar surface achieves. This multi-wavelength signature confirms that the enormous luminosity originates from accretion onto a compact central object, rather than star formation or other processes. A galaxy undergoing intense star formation can also produce tremendous luminosity, but the spectral characteristics differ systematically from those of quasar emission. The X-ray brightness, the specific shape of the ultraviolet continuum, and the presence of broad emission lines from rapidly moving gas all point toward a central engine powered by accretion. The rate at which TON 618 consumes surrounding matter remains uncertain but clearly enormous by cosmic standards. Sustaining the observed luminosity requires converting mass into radiation at rates that depend on the assumed efficiency. For 10% efficiency, roughly several hundred solar masses per year must flow through the accretion disk. For higher efficiencies achieved by rapidly spinning black holes, somewhat lower accretion rates would suffice. This consumption rate exceeds the total stellar mass of many small dwarf galaxies every few million years. The fuel reservoir required to sustain such activity over significant cosmic timescales represents a substantial fraction of the gas content of even massive galaxies. Either TON 618 has access to an exceptional supply of infalling material, or the current high luminosity phase represents a transient state within a longer history of varying activity. Such high accretion rates cannot persist indefinitely. The reservoir of gas available for consumption, even in the most massive galaxies, is finite. Major galaxy mergers can drive fresh gas toward galactic centers, potentially triggering or re-triggering quasar activity. But between such events, the gas supply gradually depletes as material either accretes onto the black hole, forms stars, or gets expelled by feedback processes. TON 618 likely experiences periods of intense activity, alternating with quieter phases when the immediate supply of accretion material runs low. The current observation captures this object during an active phase, which creates selection bias in surveys. Inactive ultramassive black holes would be essentially invisible at cosmological distances. They would sit quietly at galactic centers, detectable only through their gravitational influence on nearby stars. We see TON 618 precisely because it happens to be accreting vigorously at the cosmic epoch we observe. The space immediately surrounding the event horizon exhibits properties unlike anything in our cosmic neighborhood. Extreme gravitational fields create conditions where both quantum mechanical effects and general relativistic effects become simultaneously important. This regime, where the two pillars of modern physics must somehow be reconciled, remains theoretically uncharted. The innermost regions of black hole environments serve as natural laboratories for physics we cannot probe through any earthbound experiment. The singularity at the center, where current physics predicts infinite density, almost certainly indicates a breakdown of our theories rather than an actual physical state. General relativity faithfully describes space-time curvature in all tested regimes, but its prediction of infinite density at black hole centers likely signals the need for a more complete theory. A working theory of quantum gravity, which physicists have sought for decades without complete success, would be required to describe what actually exists at the center of TON 618. What exists at that center remains one of the deepest unsolved problems in physics. The singularity theorems proven by Penrose and Hawking in the 1960s and 70s demonstrate that singularities are inevitable consequences of general relativity, given certain reasonable assumptions about matter. But these theorems tell us only that the theory predicts singularities, not what physical reality replaces them when quantum effects become important. The boundary conditions at the event horizon present their own theoretical puzzles. Information that crosses this boundary becomes inaccessible to outside observers. According to classical general relativity, this information is simply lost, excised from the external universe forever. Yet quantum mechanics requires that information be preserved, that the complete quantum state of a system remain determinable in principle from later measurements. This conflict between general relativity and quantum mechanics, known as the black hole information paradox, remains actively debated after 5 decades of theoretical work. Proposed resolutions range from subtle correlations in the Hawking radiation that black holes emit, allowing information to gradually leak out, to radical revisions of our understanding of space-time structure, suggesting that information never truly crosses the horizon, or that the interior connects to other regions through quantum effects. TON 618 exists in a state that will persist for timescales that dwarf the current age of the universe. Hawking radiation, the quantum mechanical process by which black holes slowly evaporate, operates on timescales proportional to the cube of the black hole mass. This cubic dependence means that more massive black holes evaporate far more slowly than less massive ones. For an object containing 66 billion solar masses, complete evaporation through Hawking radiation would require a time span exceeding 10 to the 100th power years. This number so vastly exceeds the current age of the universe, approximately 14 billion years or roughly 10 to the 10th power years, that no meaningful comparison exists. The current cosmos represents less than an infinitesimal fraction of the time required for TON 618 to evaporate. Every structure in the present universe, from stars to galaxies to superclusters, will long since have vanished before this black hole even begins significant mass loss through Hawking processes. The physical reality of TON 618 encompasses phenomena ranging from the familiar to the utterly exotic, energy conversion processes operate at efficiencies no other cosmic phenomenon matches. The gravitational potential energy of infalling matter transforms into radiation with conversion factors that make nuclear fusion look wasteful by comparison. Gravitational fields achieve intensities found nowhere else in the observable universe outside black hole environments. The curvature of space-time reaches values that would have seemed physically impossible before Einstein's theory revealed their necessity. Space-time geometry warps in ways that violate everyday intuition about space and time as separate, absolute concepts. Einstein taught us that space and time form a unified fabric, curved by mass and energy. Near TON 618, this lesson achieves its most dramatic demonstration. Time runs at different rates at different locations. Space curves so severely that straight lines no longer exist in any conventional sense. The familiar geometry of Euclid, adequate for terrestrial architecture and navigation, fails completely. Yet despite this exotic nature, TON 618 obeys the same physical laws that govern falling apples and orbiting planets. General relativity, formulated by Einstein over a century ago in a patent office and university setting far removed from astronomical observation, successfully describes the space-time geometry around objects of almost inconceivable mass located at cosmological distances. Conservation laws for energy, momentum, and angular momentum dictate the behavior of accreting matter exactly as they dictate the behavior of familiar objects on Earth. This continuity of physical law provides the foundation for everything scientists claim to know about TON 618. The measurements, the mass estimates, the models of accretion disk structure and energy output all rest on assuming that physics operates consistently throughout the observable universe and throughout cosmic time. The light reaching us from TON 618 departed over 10 billion years ago, when the universe was young and different in many ways. Yet we confidently apply physics developed on Earth in the 20th and 21st centuries to interpret that ancient light. Every observation consistent with these theoretical predictions strengthens confidence in the fundamental framework. When the multi-wavelength spectrum matches accretion disk models, when the emission line widths correspond to expected orbital velocities, when the luminosity falls within ranges permitted by Eddington limits on accretion rates, each confirmation adds support to the edifice of physical understanding. Simultaneously, the search continues for any deviation that might reveal new physics beyond current understanding. The physical dominion of TON 618 extends from the quantum scale at its central singularity through the relativistic environment of its event horizon and inner accretion disk, outward through the sphere of gravitational influence dominating stellar orbits, and further still through jet activity that deposits energy across intergalactic distances. This single object, invisible at its core yet brilliant in its surrounding emission, shapes the cosmos across scales spanning more than 20 orders of magnitude. From the Planck scale, where quantum gravity presumably operates to the megaparsec scales of jet-driven feedback, TON 618 demonstrates the physical principles that govern the universe at its most extreme. Measuring the mass of a black hole presents a fundamental challenge that astronomers have addressed through multiple independent techniques over several decades of painstaking observation and theoretical development. The black hole itself emits no radiation. The event horizon provides no direct signal that any instrument could detect. No probe can approach close enough to sample the gravitational field directly. All information about the central mass must be extracted from observations of surrounding matter whose behavior reflects the gravitational influence of the unseen object. This situation resembles trying to determine the mass of an invisible person by watching how objects move around them. If you observe a heavy ball swinging in a circle at the end of an invisible rope held by an invisible figure, you can calculate how strong that figure must be to maintain the circular motion. The physics connecting circular motion to central force is well understood. Apply that physics to astronomical observations, and you can weigh objects you cannot see. The primary method for estimating the mass of TON 618 employs a technique called reverberation mapping, an elegant approach that exploits the finite speed of light to measure distances within systems too compact to resolve directly. The basic principle relies on the light travel time between different emitting regions around an active black hole. Understanding this technique requires understanding the structure of matter surrounding actively accreting supermassive black holes. The accretion disk close to the black hole produces intense ultraviolet and optical radiation. This central emission varies in brightness over time, as instabilities and inhomogeneities in the accretion flow cause fluctuations. The variations occur on timescales of days to weeks, reflecting the dynamical timescales in the inner disk regions. Monitoring these variations provides the first component of the reverberation mapping technique. Farther from the black hole, clouds of gas orbit at greater distances. These clouds contain atoms that absorb the intense radiation from the central accretion disk and re-emit it at characteristic wavelengths. The emission lines from these clouds, particularly lines from ionized carbon, magnesium, and hydrogen, provide crucial diagnostics of the physical conditions and velocities in the surrounding gas. When the central accretion disk brightens, the surrounding gas clouds respond by emitting more strongly. But this response does not occur instantaneously. Light from the central source must travel outward to reach the gas clouds before they can respond. This light travel time introduces a measurable delay between variations in the central continuum emission and corresponding variations in the emission line brightness from the surrounding clouds. By monitoring how the brightness of different emission features varies over time, astronomers can measure this delay and thereby determine the physical size of the emitting region. If the continuum brightens and the emission lines respond 3 weeks later, the clouds must lie approximately 3 light weeks from the central source. This distance measurement, derived purely from timing observations, requires no assumptions about cosmological distances or angular sizes. The second component of reverberation mapping comes from spectroscopy. The emission lines from the orbiting gas clouds are not narrow spikes at single wavelengths. They appear broadened, spread across a range of wavelengths by the Doppler effect. Gas moving toward us emits light that appears blue-shifted to shorter wavelengths. Gas moving away emits light that appears red-shifted to longer wavelengths. The total width of the emission line reflects the range of velocities present in the emitting gas. For TON 618, spectroscopic observations reveal emission lines with widths corresponding to velocities exceeding 10,000 km per second. This velocity represents roughly 3% of the speed of light. Material moving this fast while remaining in bound orbits requires an extremely massive central object to provide sufficient gravitational attraction. Without adequate central mass, such rapidly moving gas would simply fly away into space. Combining the size measurement from reverberation timing with the velocity measurement from emission line widths allows calculation of the central mass through straightforward application of gravitational physics. The fundamental relationship is elegant in principle and traces back to Newton's laws of motion combined with his law of universal gravitation. If gas orbits at velocity v at a distance r from a central mass m, then gravitational attraction provides the centripetal force maintaining the orbit. The gravitational force equals the mass times the centripetal acceleration required for circular motion at that velocity and radius. This relationship allows solving for m given measurements of v and r. The reverberation mapping technique provides exactly these measurements for material orbiting active supermassive black holes at cosmological distances. For TON 618, the combination of measured velocities and estimated orbital radii points toward a central mass in the tens of billions of solar masses. The specific value depends on details of the analysis, including assumptions about the geometry of the emitting region and calibration factors derived from comparing reverberation results to other mass measurement techniques in nearby galaxies. The uncertainty in this measurement arises from multiple sources that honest scientific analysis must carefully consider. The geometry of the emitting region affects how measured velocities translate to actual orbital velocities. Spectroscopic observations provide only the line-of-sight component of velocity. Gas moving perpendicular to our line of sight contributes nothing to the observed Doppler shift despite having substantial actual velocity. If the gas clouds orbit in a flattened disk viewed face-on, Most of the orbital motion occurs perpendicular to our line of sight, and the observed velocities underestimate the true orbital speeds. If viewed edge-on, the full orbital velocity projects along our line of sight. The inclination angle of the system, generally unknown for distant quasars, introduces systematic uncertainty in the mass derivation. Additional complications arise if the gas moves primarily radially rather than in circular orbits. Inflowing or outflowing material produces Doppler shifts that could be misinterpreted as orbital motion. The broad emission lines from quasars likely contain contributions from multiple kinematic components, including orbital motion, inflow, outflow, and turbulence. Disentangling these contributions requires modeling that introduces further assumptions and uncertainties. Calibration of the reverberation mapping method relies on comparing results to more direct mass measurements in nearby galaxies, where stellar dynamics can be observed. In galaxies close enough for individual stars near the center to be tracked, their orbital motions directly reveal the central mass without requiring assumptions about gas kinematics. Comparing reverberation masses to stellar dynamical masses for the same objects establishes a calibration factor that accounts for the average effects of geometry and kinematics. This calibration introduces additional uncertainty, as the relationship established for local supermassive black holes may not perfectly extend to the ultramassive regime where TON 618 resides. The calibration sample contains no objects with masses approaching 66 billion solar masses, simply because no such nearby objects exist. Extrapolating the calibration to this extreme mass range assumes that the same relationships hold, an assumption that cannot be directly verified. A secondary technique estimates black hole mass from the total luminosity of the quasar combined with empirical relationships between luminosity and mass established from studying many systems. This approach rests on the concept of the Eddington limit, a theoretical maximum luminosity that any object of given mass can sustain. The Eddington limit arises from the balance between gravitational attraction, pulling material inward, and radiation pressure, pushing material outward. As a black hole accretes more rapidly, it produces more radiation. This radiation exerts outward pressure on surrounding gas through interactions between photons and electrons. At sufficiently high luminosity, the outward radiation pressure exceeds the inward gravitational pull, blowing away the fuel supply and halting accretion. This limiting luminosity depends directly on mass. More massive black holes have stronger gravity that can overcome greater radiation pressure, allowing higher luminosities before the blow-away limit is reached. The Eddington luminosity scales linearly with mass, providing a direct link between how bright an accreting black hole appears and how massive it must be. More massive black holes can sustain higher accretion rates without exceeding this theoretical limit, allowing them to produce greater luminosities. The exceptional brightness of TON 618 therefore suggests exceptional mass, consistent with the reverberation mapping results. An object radiating at 140 trillion solar luminosities must contain tens of billions of solar masses to avoid exceeding its Eddington limit. This luminosity-based approach carries its own distinct uncertainties. The relationship between luminosity and mass shows significant scatter among measured systems. Not all black holes accrete at the same fraction of their Eddington limit. Some objects accrete at only a few % of the maximum rate, appearing much fainter than their mass would suggest. Others may briefly exceed the nominal Eddington limit through geometric effects that allow radiation to escape preferentially in certain directions. Factors including the instantaneous accretion rate, the radiative efficiency determined by black hole spin and disk geometry, and the viewing angle all affect the observed brightness independently of the black hole mass. A black hole viewed down the axis of its accretion disk appears brighter than the same object viewed edge-on, even though the intrinsic properties are identical. While the extremely high luminosity of TON 618 strongly suggests an extremely massive central engine, the precise mass derived from luminosity alone would carry large uncertainty. The combination of multiple independent techniques strengthens confidence in the mass estimate far beyond what any single method could provide. When reverberation mapping and luminosity-based methods yield consistent results pointing toward the same mass range, this agreement suggests that neither method suffers from large systematic errors that would bias them in opposite directions. The convergence of different approaches toward masses in the range of 40 to 70 billion solar masses provides the foundation for current scientific understanding of TON 618. Additional constraints come from theoretical limits on how massive a black hole can grow within the available cosmic time. TON 618 appears as it existed over 10 billion years ago, when the universe was only approximately 3 billion years old. This ancient cosmic epoch places demanding constraints on any black hole observed at such great distance. Any black hole observed at this early time has had limited opportunity to grow from whatever seed mass initiated its formation. Black holes cannot simply appear fully formed at arbitrary masses. They must grow from smaller seeds through accretion or mergers, processes that require time to accumulate the necessary mass. The existence of a 66 billion solar mass black hole when the universe was young challenges theories of black hole formation and growth. Theoretical models suggest that black holes can grow through accretion at rates limited by the Eddington balance between gravity and radiation pressure. Even accreting continuously at this maximum rate, growth proceeds at a pace that places firm constraints on achievable masses. The characteristic growth timescale at the Eddington limit, sometimes called the Salpeter time, equals roughly 45 million years. Starting from a stellar mass seed of perhaps 100 solar masses and growing continuously at the Eddington limit would require approximately 20 doublings to reach 1 billion solar masses. Each doubling takes roughly 45 million years, so reaching 1 billion solar masses requires nearly 1 billion years of continuous maximal accretion. Growing to 66 billion solar masses would require an additional 6 doublings, adding another 250 million years minimum. This calculation reveals the challenge. Even starting immediately after the Big Bang with a 100 solar mass seed and accreting continuously at the maximum possible rate without interruption, reaching 66 billion solar masses by the time we observe, TON 618 remains marginally possible but leaves essentially no room for delays. Any period of reduced accretion, any interval without adequate fuel supply, would make achieving this mass impossible within the available time. Several theoretical mechanisms might allow faster growth. Super Eddington accretion represents one possibility. Under certain conditions, radiation produced in the inner accretion disk can become trapped and advected inward with the infalling gas rather than escaping to exert outward pressure. This trapping occurs when the accretion rate becomes so high that photons cannot diffuse outward faster than they are carried inward by the flowing material. Without the outward radiation pressure, accretion can proceed at rates exceeding the standard Eddington limit. Super Eddington accretion could accelerate mass accumulation significantly, potentially by factors of 10 or more above the standard limit. However, such extreme accretion rates require exceptional fuel supplies and may be self-limiting as the intense radiation eventually clears away surrounding material. Whether sustained Super Eddington growth can explain the most massive early black holes remains an active area of theoretical investigation. Alternatively, mergers between massive black holes could rapidly increase mass without requiring sustained accretion. When two galaxies merge, their central black holes eventually sink to the center of the merger remnant and coalesce into a single larger black hole. This process adds mass instantaneously, limited only by how massive the progenitor black holes were and how frequently mergers occur. The observed population of ultramassive black holes in the early universe provides empirical constraints that theorists continue working to explain. Each new discovery of an extremely massive black hole at high redshift tightens the requirements on formation models. The existence of objects like TON 618 demonstrates that nature found ways to build such extreme masses early in cosmic history, even if the precise mechanisms remain under debate. The mass estimate for TON 618 must be understood within the context of other extremely massive black holes that compete for the title of largest known. The designation of largest reflects current measurements with their associated uncertainties, rather than definitive cosmic rankings. Several objects have mass estimates overlapping with or potentially exceeding the commonly cited value for TON 618. Phoenix A represents one prominent competitor. This central black hole in the Phoenix galaxy cluster has estimated mass approaching 100 billion solar masses according to some analyses. Located roughly 5.5 billion light-years from Earth, Phoenix A resides in a massive galaxy at the center of a cooling flow cluster where large amounts of gas flow toward the central regions. The mass measurement for Phoenix A derives from the motions of stars and gas near the galactic center, providing a somewhat different methodology than the reverberation mapping applied to TON 618. Stellar dynamical measurements track the velocities of individual stars or the integrated starlight from the central stellar population. These velocities reveal the gravitational potential and hence the enclosed mass. The uncertainty ranges for Phoenix A and TON 618 overlap substantially. Depending on which measurements and analysis methods one prefers, either object could plausibly claim the title of most massive known black hole. This overlap reflects the genuine difficulty of measuring black hole masses at cosmological distances rather than indicating poor quality observations. Both measurements represent state-of-the-art applications of the best available techniques. Holmberg 15. A hosts another central black hole, with mass estimates reaching 40 billion solar masses based on stellar dynamical modeling. This relatively nearby object, located roughly 700 million light-years from Earth, allows detailed study of the central stellar population. The large mass estimate places Holmberg 15A among the most massive black holes with reliable measurements, though still below the extreme upper end occupied by TON 618 and Phoenix A. IC 1101, one of the largest known galaxies, likely contains a central black hole that could rival TON 618 in mass. This supergiant elliptical galaxy contains trillions of stars and spans several million light-years in diameter. However, direct measurements of its central black hole remain limited by the galaxy's great distance and the challenge of resolving central stellar dynamics at over 1 billion light-years. The mass estimates for IC 1101 rely primarily on scaling relationships between black hole mass and host galaxy properties. Given the extraordinary size and mass of the host galaxy, the central black hole should be correspondingly extreme. But without direct dynamical measurements, these estimates carry greater uncertainty than objects like TON 618, where spectroscopic observations probe the immediate black hole environment. The competition for largest known black hole reflects not only genuine variation in cosmic populations, but also the different systematic uncertainties affecting various measurement techniques. A black hole measured through stellar dynamics in a relatively nearby galaxy faces different potential biases than one measured through reverberation mapping of a distant quasar. Direct comparison requires carefully accounting for these methodological differences. Stellar dynamical measurements offer the advantage of observing gravitationally bound stellar orbits that follow well-understood Keplerian physics. Stars are not subject to the radiation pressure effects, outflows, and complex gas dynamics that complicate interpretation of gas kinematics. However, stellar dynamical measurements require resolving individual stellar motions or integrated stellar velocity dispersions in the innermost galactic regions, which becomes increasingly difficult at greater distances. Reverberation mapping works at cosmological distances where stellar dynamics cannot be resolved, making it the only viable technique for extremely distant quasars like TON 618. But the interpretation of gas kinematics introduces uncertainties that stellar dynamical methods avoid. Each technique has strengths and limitations that must be understood when comparing mass estimates derived through different approaches. Recent improvements in observational capabilities continue refining mass estimates for extreme black holes. The Event Horizon Telescope demonstrated the ability to directly image the immediate surroundings of supermassive black holes, at least for relatively nearby examples. The famous image of the black hole shadow in Messier 87 provided a mass estimate consistent with prior stellar dynamical measurements, validating both techniques. Future facilities with improved sensitivity and angular resolution may extend such direct imaging to more distant and more massive objects. The planned next-generation Event Horizon telescope would increase the number of participating radio dishes and extend baselines to include orbital platforms. Such improvements could potentially resolve the shadow regions around more distant black holes, providing direct mass measurements that sidestep many uncertainties in current techniques. Spectroscopic surveys identifying new high-luminosity quasars regularly discover candidates for extremely massive central black holes. Each discovery adds to the statistical understanding of the ultramassive black hole population and occasionally reveals individual objects that might challenge current record holders. The Sloan Digital Sky Survey and its successors have identified thousands of quasars, many with luminosities suggesting extremely massive central engines. The James Webb Space Telescope brings new capabilities for studying distant quasars in unprecedented detail. Infrared observations can penetrate dust that obscures some systems at optical wavelengths. The rest frame ultraviolet emission from high redshift quasars shifts into the infrared by the time it reaches Earth, making Webb ideally suited for studying the most distant active black holes. Webb's spectroscopic capabilities allow measurement of emission line profiles with sensitivity and resolution exceeding previous infrared facilities. These measurements provide velocity information for reverberation mapping and related techniques. Early results from Webb have already improved understanding of black hole demographics in the early universe, identifying surprisingly massive black holes at redshifts, previously inaccessible to detailed study. What the competition for largest known black hole ultimately reveals is that objects like TON 618 exist as members of a population rather than unique cosmic oddities. The universe apparently produces ultramassive black holes through processes that remain incompletely understood, but clearly operate efficiently in at least some cosmic environments. Finding multiple objects with masses in the tens of billions of solar masses indicates that whatever growth mechanisms operate can achieve extreme results repeatedly. The statistical distribution of black hole masses provides crucial information about formation and growth mechanisms that individual measurements cannot provide. If ultramassive black holes like TON 618 represent extremely rare outliers, this suggests different physical processes than if they constitute the high mass tail of a continuous distribution extending smoothly from smaller supermassive black holes. Current data suggest that the most massive black holes reside preferentially in the most massive galaxies and galaxy clusters. The correlation between black hole mass and host galaxy properties extends across several orders of magnitude, from black holes of millions of solar masses in relatively modest galaxies to black holes of tens of billions of solar masses in the most massive galaxies known. This correlation supports models where black hole growth proceeds in parallel with galaxy assembly, with the most extreme growth occurring in the most extreme environments. Galaxy clusters represent the densest cosmic environments where the most massive galaxies form through repeated mergers over cosmic time. The central galaxies in such clusters provide the most favorable conditions for black hole growth through both enhanced accretion rates and frequent black hole mergers accompanying galaxy mergers. The host galaxy of TON 618, though difficult to observe directly due to the overwhelming quasar luminosity, likely represents one of the most massive galaxies existing at that cosmic epoch. The correlations observed at lower redshifts suggest that the extreme black hole mass requires an extreme host. Such hosts would be rare at any cosmic epoch, and rarer still in the younger universe when TON 618 shone most brightly. The uncertainty in mass measurements for the most extreme black holes means that the title of largest known could shift as techniques improve and new observations accumulate. TON 618 holds the commonly cited record based on current best estimates, but this designation reflects the present state of astronomical knowledge rather than a definitively established cosmic fact. Future observations might revise the mass estimate upward or downward, or might identify other objects whose masses exceed the current best estimate. What remains robust across all measurements and methods is that black holes containing tens of billions of solar masses exist and were already present when the universe was relatively young. This observational fact constrains theories of cosmic structure formation regardless of which specific object ultimately proves most massive. Any viable theory must explain how such extreme objects could form and grow within the available cosmic time. The theoretical challenge has intensified with each discovery of massive black holes at higher redshifts. Black holes approaching 1 billion solar masses have been found at redshifts corresponding to cosmic ages of less than 1 billion years. These discoveries require either very massive initial seeds, super Eddington accretion rates, or frequent mergers, or some combination of all three. Standard models that begin with stellar mass seeds and grow at the Eddington limit cannot explain the observed population. Various theoretical proposals address this challenge. Direct collapse black holes might form from primordial gas clouds that avoided fragmenting into stars, instead collapsing directly into black holes of 10,000 to 100,000 solar masses. Such massive seeds would require fewer doublings to reach ultramassive scales. Alternatively, dense stellar clusters in the early universe might have produced intermediate mass black holes through runaway stellar collisions and mergers, providing seeds more massive than ordinary stellar remnants. The challenge of measuring invisible objects across cosmological distances pushes observational astronomy to its limits. Every mass estimate represents a triumph of indirect reasoning, applying physical laws established through earth-bound experiments to infer properties of objects utterly unlike anything in human direct experience. The chains of inference connecting observed photons to derive black hole masses involve multiple steps, each introducing potential uncertainties and systematic effects. Scientists using these techniques remain acutely aware of the limitations. The uncertainties acknowledged in published measurements reflect not failure, but appropriate scientific humility about the limits of current knowledge. Reporting that TON 618 contains 66 billion solar masses with an uncertainty range spanning from 40 to 70 billion. Solar masses honestly represents what the data actually constrain. The history of astronomical measurement includes numerous examples where initial estimates required substantial revision as techniques improved. Early distance measurements to galaxies were wrong by factors of 2 or more before the cosmic distance ladder became well calibrated. Mass estimates for the most extreme objects may similarly require revision as better observations become available and systematics become better understood. What we can state with confidence is that TON 618 belongs firmly among the most massive black holes ever detected. Whether it contains exactly 66 billion solar masses or somewhat more or less, it represents an extreme outlier in the cosmic population. The measurement techniques that reveal its extraordinary nature, despite their limitations, provide our only window into the properties of objects that remain forever invisible by their fundamental nature. The techniques themselves represent remarkable human achievements. Reverberation mapping transforms timing measurements of brightness variations into distance estimates. Spectroscopy decodes velocity information from the subtle shifting of wavelengths. Gravitational theory connects observed motions to inferred masses. Together, these tools allow weighing objects that emit no light, located at distances so great that the light reaching us today departed billions of years before Earth formed. The continuing improvement of these techniques, through better instruments, longer monitoring campaigns, more sophisticated analysis methods, and careful attention to systematic effects, will refine our understanding of the most massive black holes in the cosmos. TON 618 will remain a benchmark object, one of the most extreme examples against which theories must be tested and measurement techniques validated. TON 618 exists not as an isolated cosmic curiosity, but as an extreme example of structures that shape the universe we observe today. Supermassive black holes reside at the centers of virtually all large galaxies, and their presence influences galactic evolution through processes that astronomers are only beginning to fully understand. The relationship between these central gravitational engines and their surrounding stellar populations represents one of the most active areas of research in modern astrophysics. When astronomers first began systematically measuring black hole masses in nearby galaxies during the 1990s, they noticed something unexpected. The masses were not randomly distributed. Instead, they correlated tightly with properties of the host galaxies, particularly the mass and velocity dispersion of stars in the central bulge region. Galaxies with more massive central bulges contained more massive central black holes, following a relationship that extends across several orders of magnitude in mass. This correlation seems impossible to explain through coincidence. The central black hole occupies a region millions of times smaller than the galactic bulge. Stars in the bulge orbit at distances where the black hole's gravity represents a negligible perturbation compared to the collective gravity of surrounding stellar populations. Yet somehow, the black hole knows how massive its surrounding galaxy should be, or the galaxy knows how massive its central black hole should be. Some physical connection must link these vastly different scales. The mechanism connecting black hole mass to host galaxy properties remains actively debated among researchers who have proposed multiple competing explanations. Understanding this connection matters for interpreting objects like TON 618, because the correlation, if it holds at extreme masses, predicts specific properties for the host galaxy that we cannot directly observe due to the overwhelming quasar luminosity. One class of models proposes that black hole feedback regulates the growth of both the black hole and the surrounding stellar population. During active accretion phases, the central black hole releases tremendous energy through radiation and mechanical outflows. This energy heats surrounding gas, potentially expelling it from the galaxy entirely, or at minimum preventing it from cooling and collapsing into new stars. When the black hole grows too massive relative to its host, the resulting feedback becomes strong enough to suppress further growth of both components. The radiation and jets from an overly massive black hole would blow away the gas supply needed for continued accretion while simultaneously preventing that same gas from forming new stars. This self-regulation could naturally produce the observed correlation, with the final masses determined by the balance point where feedback matches the binding energy of gas in the galactic potential well. The feedback model explains several observed phenomena beyond the mass correlation itself. Many massive galaxies appear surprisingly devoid of ongoing star formation, despite containing substantial reservoirs of hot gas. This gas should cool and collapse into stars on timescales shorter than the age of the universe. Yet observations show that cooling is somehow suppressed. Energy injection from central black holes provides a natural explanation, with periodic active phases reheating the gas before it can form stars. Radio observations reveal that many central black holes produce jets that inflate enormous cavities in the surrounding hot gas. These cavities, visible as regions of reduced X-ray emission, represent direct evidence of energy transfer from the black hole to the galactic environment. The energy contained in these cavities often matches the energy deficit required to prevent gas cooling, suggesting that black hole feedback operates at precisely the level needed to maintain thermal balance. Alternative models suggest that common external factors drive both black hole and galaxy growth without requiring direct causal connection. Major galaxy mergers represent the most dramatic events in galactic evolution, bringing together two separate stellar systems and their associated gas reservoirs into a single, more massive remnant. These mergers funnel gas toward the galactic center through gravitational torques and dynamical friction. The gas driven toward the center during mergers serves dual purposes. Some portion forms new stars in the central bulge region, building up the stellar mass concentration. Another portion falls toward the central black hole, fueling accretion and growing the black hole mass. The amount of gas involved in such mergers might determine both the final stellar mass of the merger remnant and the final mass of the central black hole, creating correlation without any direct feedback mechanism. This merger-driven model explains why the correlation exists but struggles to explain the tightness of the observed relationship. Random variations in merger histories, gas fractions, and orbital parameters should introduce substantial scatter around any mean correlation. The observed relationship appears tighter than naive merger models predict, suggesting that some additional regulatory mechanism operates. Current understanding suggests that both feedback and merger-driven growth contribute to establishing the observed correlations. Mergers provide the gas supply that enables growth, while feedback regulates how efficiently that gas converts into black hole mass versus stellar mass. The relative importance of these mechanisms may vary with galaxy mass, cosmic epoch, and environmental factors in ways that ongoing research continues to explore. For ultramassive black holes like TON 618, these regulatory mechanisms must have operated under extreme conditions during the early universe. The observed mass-to-bulge relationship, if it extends to such extreme masses, predicts that the host galaxy should contain stellar mass comparable to or exceeding the most massive galaxies in the local universe. Such systems represent the extreme environments where cosmic structure formation proceeded most vigorously. The most massive galaxies known in the present-day universe contain stellar masses approaching 10 trillion solar masses. These supergiant elliptical galaxies reside at the centers of rich galaxy clusters, built up through countless mergers over cosmic time. If TON 618 follows the standard correlations, its host galaxy should rival or exceed these extreme systems despite existing when the universe was only a few billion years old. Building such a massive galaxy so early in cosmic history presents its own theoretical challenges, independent of the difficulty of growing the central black hole. The hierarchical model of structure formation predicts that massive galaxies assemble gradually through mergers of smaller progenitors. Forming a 10 trillion solar mass galaxy within the first few billion years requires exceptionally rapid assembly from an unusually dense cosmic environment. The early universe provided conditions that may have favored rapid growth of both black holes and their host galaxies. Higher cosmic matter density meant more gas available for both star formation and black hole accretion. The universe at a redshift corresponding to TON 618 was roughly 10 times denser than today, with gas distributed in structures that had not yet been consumed by earlier generations of star formation. More frequent galaxy mergers provided mechanisms for funneling material toward galactic centers. The higher density environment meant that galaxies encountered each other more often, triggering the gravitational interactions that drive gas inward. Each merger potentially triggered both a starburst episode building the bulge and an active galactic nucleus phase growing the black hole. The absence of heavy elements that later enable efficient radiative cooling may have paradoxically allowed more rapid accretion in some circumstances. When gas cools efficiently, it fragments into dense clumps that form stars rather than feeding the central black hole. In pristine primordial gas lacking the carbon, oxygen, and other cooling agents produced by stellar nucleosynthesis, fragmentation is suppressed. Larger masses of gas can fall toward the center without fragmenting, potentially enabling more rapid black hole growth. Theoretical models propose various pathways for creating the seed black holes that eventually grew into ultramassive objects like TON 618. The standard pathway begins with stellar mass black holes formed from the first generation of massive stars. These population 3 stars, formed from pristine hydrogen and helium gas, may have reached masses of several hundred solar masses before exploding or collapsing directly into black holes. A stellar mass seed of 100 solar masses could grow to ultramassive scales through sustained accretion, but the timescales involved challenge standard models as discussed in previous sections. The Eddington limited growth time barely suffices to reach 66 billion solar masses, even starting immediately after the first stars formed and accreting continuously without interruption. Direct collapse black holes represent an alternative seeding mechanism that provides more massive initial conditions. Under special circumstances, primordial gas clouds might collapse directly into black holes without fragmenting into stars. These special conditions require suppression of molecular hydrogen cooling, which typically enables gas to cool and fragment at temperatures of a few hundred degrees. Intense ultraviolet radiation from nearby star-forming regions can dissociate molecular hydrogen, preventing this cooling channel. If the radiation field is strong enough, gas clouds cannot cool efficiently and instead collapse monolithically when they reach a critical mass. Computer simulations suggest that such direct collapse could produce black holes of 10,000 to 100,000 solar masses, providing a substantial head start compared to stellar mass seeds. Starting from a direct collapse seed of 100,000 solar masses, rather than a stellar seed of 100 solar masses, reduces the required number of mass doublings by approximately 10. This relaxes the constraints on growth timescales considerably, making ultramassive black holes at early cosmic epochs much easier to explain theoretically. Dense stellar clusters might produce intermediate mass black holes through a third mechanism involving runaway stellar mergers. In sufficiently dense cluster cores, stellar collisions occur frequently enough that the most massive stars continually merge with their neighbours before they can explode as supernovae. This runaway process can build up stellar masses of several thousand solar masses before the merged object finally collapses into a black hole. Sequential black hole coalescence within clusters provides yet another pathway. After the first black holes form from massive stars, dynamical friction causes them to sink toward the cluster center where they encounter and merge with each other. Each merger roughly doubles the black hole mass while releasing energy in gravitational waves. Repeated mergers can build up black holes of hundreds or thousands of solar masses within cluster environments. The existence of ultramassive black holes at high redshift challenges all proposed formation scenarios to some degree. Each pathway requires specific conditions that may or may not have been common in the early universe. Direct collapse requires special radiation environments that simulations suggest were rare. Runaway stellar mergers require cluster densities that may have been difficult to achieve. Standard stellar seeds require sustained accretion rates that approach or exceed theoretical limits. The observed population of massive black holes at high redshift increasingly constrains which formation scenarios remain viable. Each new discovery tightens the requirements that successful theories must satisfy. The existence of objects like TON 618 demonstrates that nature found ways to build such extreme masses early in cosmic history, providing empirical guidance for theoretical model development. TON 618's extreme mass therefore carries information about cosmic conditions and physical processes operating in the early universe that we cannot directly observe. The black hole serves as a fossil record of growth conditions that prevailed when the universe was young. Measuring such objects precisely helps constrain which formation pathways operated efficiently and which require modification or abandonment. The distribution of black hole masses throughout cosmic history provides a broader fossil record of galaxy evolution. Black holes can only grow through accretion and mergers. They cannot shrink through any known process on cosmologically relevant timescales. Hawking evaporation operates far too slowly to affect stellar mass or larger black holes within the current age of the universe. The mass of a black hole today therefore represents the accumulated growth since its formation, integrating over all accretion episodes and merger events throughout cosmic time. This irreversibility makes black holes unique among astronomical objects as tracers of cosmic history. Stars can form and die, returning material to the interstellar medium. Gas can cycle between hot and cold phases, between galaxies and intergalactic space, but mass that enters a black hole remains there permanently, recording the integrated fuel supply that the black hole accessed throughout its existence. Observations of quasars at various cosmic epochs reveal how the active black hole population evolved over cosmic time. Quasar surveys spanning billions of light-years in look-back time show that the quasar population peaked when the universe was roughly 2 to 3 billion years old. Both the number density of luminous quasars and their average luminosity were higher during this cosmic epoch than at any time before or since. This peak in quasar activity corresponds to a peak in the cosmic star formation rate, suggesting common drivers for both phenomena. The same gas supplies that fuel black hole accretion also form new stars. The merger activity that triggers quasar phases also triggers starbursts. The coordinated evolution of black hole accretion and star formation supports models where these processes are fundamentally linked rather than independent. Following the peak epoch, both quasar activity and cosmic star formation decline toward the present day. This evolution reflects the declining availability of fuel for both processes as galaxies consumed their gas reservoirs. Star formation converted gas into stars. Black hole accretion converted gas into black hole mass and radiated energy. Galactic winds driven by supernovae and active galactic nuclei expelled gas into intergalactic space, where it became unavailable for either process. The declining cosmic matter density due to expansion contributed as well. As the universe expanded, structures became more isolated from each other. Merger rates declined as galaxies moved apart. Gas accretion rates from the intergalactic medium onto galaxies decreased as that medium thinned. The conditions that enabled rapid growth in the early universe gradually faded as the cosmos aged. TON 618 represents a snapshot from near the peak epoch of quasar activity. We observe it as it existed over 10 billion years ago, during the cosmic period when supermassive black holes were growing most rapidly and producing the most luminous radiation. The quasar we see was one of the brightest objects in the young universe, visible across the observable cosmos despite the vast distances involved. The same object today, evolved through 10 billion additional years of cosmic time, would appear very different. Accretion presumably slowed dramatically as the gas supply depleted. Without fuel, the brilliant quasar radiation would have faded. The black hole that once powered one of the most luminous objects in existence would have become a quiescent dark mass, detectable only through gravitational effects on surrounding stars. The host galaxy would have continued evolving through this same interval. Star formation would have gradually ceased as gas supplies exhausted. The stellar population would have aged, with the most massive stars dying first and leaving behind an increasingly old, red population. Mergers with smaller galaxies would have added mass while disrupting structure. The galaxy we would observe today, if we could somehow identify it, would bear little resemblance to the star-forming system that fed the quasar 10 billion years ago. This temporal evolution connects observations of distant quasars to observations of quiescent massive galaxies in the local universe. The brilliant quasars visible at high redshift are the progenitors of the massive elliptical galaxies we observe nearby. The extreme black holes powering those ancient quasars still exist at the centers of their evolved host galaxies, now dark and quiet after billions of years without substantial fuel supply. The fate of ultramassive black holes in the far cosmic future involves timescales that dwarf the current age of the universe. Current cosmological models predict continued expansion driven by dark energy, with the universe becoming increasingly cold and empty over the coming billions and trillions of years. Within this evolving cosmic context, black holes will play an increasingly dominant role. Galaxy mergers will continue bringing new material within reach of central black holes for many billions of years, though at declining rates as expansion isolates structures from each other. The eventual merger of the Milky Way and Andromeda galaxies, predicted for approximately 4.5 billion years hence, will likely trigger renewed activity in the resulting combined supermassive black hole. Gas shocked by the collision will flow toward the new galactic center, potentially powering a brief quasar phase in our cosmic neighborhood. On longer timescales, gravitational wave emission from orbiting black hole binaries will cause massive black holes to spiral together and merge following major galaxy collisions. When two galaxies containing supermassive black holes merge, the black holes initially orbit each other at large separations. Dynamical friction against the stellar background causes their orbits to shrink gradually over hundreds of millions of years. As the separation decreases, gravitational wave emission becomes increasingly efficient at extracting orbital energy. The final coalescence occurs in a burst of gravitational radiation lasting only seconds, converting a significant fraction of the combined black hole rest mass into ripples in spacetime. These mergers represent the most energetic events in the universe, releasing more energy in moments than entire galaxies emit over millions of years. The resulting merged black holes will sit at the centers of massive elliptical galaxies, growing slowly through occasional accretion of stellar material. Stars passing too close to the black hole will be tidally disrupted, with roughly half their mass eventually accreting onto the black hole. These tidal disruption events provide occasional fuel injection, but at rates far below the vigorous accretion that powered ancient quasars. Eventually, as star formation ceases throughout the universe and stellar populations age and disperse, even this slow growth will stop. The black holes will remain as the most massive gravitationally bound objects in existence, persisting long after the stars that once surrounded them have died. White dwarfs will cool into dark cinders. Neutron stars will gradually lose their magnetic fields, but black holes will endure essentially unchanged for timescales that make stellar lifetimes look instantaneous. On truly cosmic timescales, Hawking radiation will cause even the most massive black holes to slowly evaporate. This quantum mechanical process, predicted by Stephen Hawking in 1974, allows black holes to emit particles at a temperature inversely proportional to their mass. More massive black holes are colder and emit radiation more slowly. For ultramassive black holes like TON 618, the evaporation timescale exceeds 10 to the 100th power years. This duration so vastly exceeds any timescale relevant to human experience or even cosmic history that meaningful comparison fails. The current age of the universe represents roughly 10 to the 10th power years. The time required for a black hole of 66 billion solar masses to evaporate exceeds this by 90 orders of magnitude. Every structure in the present universe, from atoms to galaxies to superclusters, will have long since transformed beyond recognition before TON 618 even begins significant mass loss. Contemplating objects like TON 618 inevitably raises questions about human significance within a universe containing such extreme phenomena. An object containing 66 billion solar masses exerting gravitational dominance over regions larger than our entire solar system, existing for timescales that render the entire history of human civilization an imperceptible instant, challenges anthropocentric perspectives on cosmic importance. The numbers involved exceed what human intuition evolved to process. Our brains developed to navigate social groups of dozens to hundreds of individuals, to track resources over seasons and years, to assess distances measured in hours of walking. Nothing in our evolutionary history prepared us to comprehend billions of solar masses, billions of light years, or billions of years. Yet humans have developed tools that extend comprehension far beyond evolved intuition. Mathematics allows manipulation of quantities that exceed direct experience. Scientific instruments detect phenomena invisible to unaided senses. Theoretical frameworks connect observations into coherent understanding that spans scales from subatomic particles to the observable universe. The very ability to measure and contemplate objects like TON 618 distinguishes human consciousness within the known universe. Through indirect reasoning and careful observation, species that evolved on one small rocky planet have mapped structures spanning billions of light years and deduced properties of objects utterly unlike anything in direct human experience. The act of measurement connects human minds to cosmic phenomena across distances and timescales that defy intuition. This capacity for comprehension represents an extraordinary development within cosmic history. The universe existed for over 9 billion years before Earth formed. Life required billions of additional years to evolve, from simple chemistry into organisms capable of abstract reasoning. Only within the last century have humans developed instruments capable of detecting quasars and techniques capable of measuring black hole masses at cosmological distances. The mathematical relationships describing black hole physics apply identically to TON 618 and to any hypothetical small black hole that might exist in our cosmic neighborhood. The same equations that Einstein formulated while working through thought experiments about falling elevators and light beams describe space-time curvature around the most massive known gravitational singularity. General relativity makes no distinction between black holes based on mass. The theory applies universally. This continuity of physical law enables the entire enterprise of observational cosmology. If physics operated differently at large scales or in distant regions, we could draw no conclusions about objects like TON 618 from observations made on Earth. The assumption that physical laws apply universally underlies every measurement and every interpretation. Every successful prediction strengthens confidence in this assumption, while the search continues for any deviation that might reveal its limitations. Science progresses through acknowledging uncertainty while building on what observations reliably establish. The mass estimate for TON 618 carries significant uncertainty, as the previous section detailed. The measurement methods involve assumptions that future observations may refine or revise. The exact value might shift upward or downward as techniques improve. But the existence of ultramassive black holes in the early universe represents a robust conclusion supported by multiple independent lines of evidence. TON 618 is not the only object in its mass class. Multiple quasars at high redshift require central engines containing tens of billions of solar masses to explain their observed luminosities. The population of such objects, not just individual measurements, constrains theories of cosmic structure formation. The questions prompted by such discoveries extend beyond astronomy into philosophy. What does it mean for humans to comprehend objects so far beyond direct experience? Our senses provide no access to black holes. We cannot see them, touch them, or directly interact with them in any way. All knowledge comes through chains of inference, connecting observations to conclusions through physical theory. Yet this indirect knowledge is genuine knowledge. We know the mass of TON 618 in the same way we know the mass of distant planets in our own solar system, through observations of gravitational effects on surrounding matter. The inference chain is longer and the uncertainties larger, but the epistemological structure is identical. If we accept that we know planetary masses, we should accept that we know black hole masses at some level of precision. How should the existence of such cosmic extremes influence perspectives on purpose, significance, or meaning? These questions lack scientific answers because science addresses how the universe works, not why it exists or what it means. But the questions emerge naturally from confrontation with cosmic scales that dwarf human concerns. One response emphasizes the remarkable nature of human understanding itself. The universe produced, through billions of years of stellar nucleosynthesis and biological evolution, creatures capable of measuring black holes at cosmological distances. Carbon forged in stellar cores billions of years ago now constitutes the brains that contemplate the nature of black holes. The cosmos has developed the capacity to understand itself through the emergence of conscious observers. This perspective does not require any supernatural or teleological interpretation. Physical processes following natural laws produced stars that produced heavy elements, that produced planets, that produced life, that produced minds capable of scientific investigation. Each step followed from prior conditions according to physical principles. Yet the result is nonetheless remarkable, a universe that has developed internal structures capable of comprehending its own nature. Another response focuses on the scale invariance of physical law. The same principles that govern falling objects on Earth describe the most extreme gravitational phenomena in the universe. This universality suggests that understanding developed through local experience can genuinely illuminate cosmic structure. Human scale investigations in laboratories and with terrestrial instruments reveal laws that apply at arbitrary scales. This universality is not logically necessary. Physics could have been scale-dependent, with different laws operating at different sizes or distances. The discovery that physics appears universal across all accessible scales represents a profound empirical finding about the nature of reality. It enables cosmology as a science and makes objects like TON 618 accessible to human investigation despite their extreme remoteness. TON 618 will continue existing long after human civilization in any recognizable form has concluded. The timescales of black hole evolution exceed not only human lifespans but the duration of biological habitability on Earth. Whatever significance humans attach to such objects exists within human minds and records rather than in the objects themselves. The black hole simply is. It warps space-time according to the equations of general relativity. It accretes matter according to the physics of gravitational collapse. It will eventually evaporate according to the principles of quantum mechanics applied to curved space-time. Purpose and meaning are categories that apply to conscious beings, not to gravitational singularities. The scientific investigation of extreme black holes continues with each new telescope and observational campaign. Future facilities will discover new candidates for most massive known object. potentially displacing TON 618 from its current position. Refined mass estimates for existing candidates will clarify which objects truly rank at the extreme end of the distribution. New techniques will probe the relationship between ultramassive black holes and cosmic structure formation in ways current capabilities cannot achieve. The questions currently debated regarding formation pathways, growth mechanisms, and the physics of extreme accretion will eventually be resolved through accumulated evidence. Theoretical models that fail to explain observations will be abandoned or modified. Successful models will be refined and extended. And the process of scientific progress will continue as it has for centuries, building reliable knowledge through the interplay of observation, theory, and critical evaluation. New questions will emerge from discoveries not yet made. Every answer in science generates new questions. Understanding how ultramassive black holes form will prompt questions about the conditions that enabled such formation. Mapping the population of extreme black holes will prompt questions about the environmental factors that produce the observed distribution. Science advances not toward final answers, but toward ever deeper questions. What remains constant is the fundamental enterprise of attempting to understand the universe through careful observation and rigorous reasoning. TON 618 represents the current frontier of this enterprise in one particular direction, marking the extreme of gravitational concentration that human instruments have successfully measured. Other frontiers exist in other directions, from the smallest particles to the largest cosmic structures, from the earliest moments to the ultimate fate of the cosmos. The black hole itself remains utterly indifferent to human attention. It consumes matter and warps space according to physical laws that operate without purpose or intention. The 66 billion solar masses compress into a region from which nothing, not light, not information, not any possible signal, can ever escape to reach external observers. This ultimate isolation distinguishes black holes from every other cosmic structure. The interior remains forever hidden, inaccessible to any observation that physics currently allows or may ever allow. Yet the exterior effects reveal the presence of something extraordinary. The brilliant quasar radiation that first attracted attention to this object, the gravitational lensing of background light, the influence on galactic structure extending far beyond the event horizon, all testify to mass concentration at scales that challenge theoretical understanding when first discovered and continue stimulating new investigation today. The universe contains objects that exist at scales fundamentally beyond direct human experience. TON 618, whether precisely 66 billion solar masses, or somewhat more or less, represents one of the most extreme examples currently known. Its existence confirms that the universe produces gravitational singularities of almost incomprehensible mass through processes that operated vigorously in the cosmic past. Measuring the invisible across billions of light years, deducing properties of objects that no human will ever directly observe, extends human understanding toward the limits of what the universe allows us to know. These limits are not arbitrary restrictions, but fundamental boundaries set by the speed of light, the age of the cosmos, and the physics of information transfer. Within these boundaries, human investigation has revealed a universe far stranger and more vast than any prior generation imagined. The remaining uncertainties in our understanding reflect not failure, but the honest boundaries of current knowledge, boundaries that future generations of astronomers will push outward through improved techniques and new discoveries. TON 618 stands as the most massive black hole currently confirmed by measurement. It may eventually yield this distinction to another object as observations continue. But its significance extends beyond any ranking to represent the remarkable human capacity for comprehending a universe filled with phenomena far stranger than unaided intuition could ever imagine. The gravitational monster at the heart of this distant quasar has consumed the equivalent of entire galaxies' worth of matter over its existence. It has warped space-time across regions larger than our entire solar system. It will persist for timescales that make the current age of the universe look like the blink of an eye. and through careful observation and rigorous reasoning, humans have measured it, understood it, and placed it within a coherent framework of cosmic evolution that connects the earliest moments of the universe to its ultimate fate in the incomprehensibly distant future.